and I'd like to present the steel industry, its transformation and evolution. Firstly, a little bit about myself. I was born in England. Obviously, I've got the accent. I'm from the northeast of England. And it has been said that I sound like Ned Stark from Game of Thrones. And it's also been said that there might be a resemblance to one or two of these guys. I mean, I don't see the resemblance myself, but anyway, moving right along. This has been a journey for myself and a journey through the steel business, spanning 44 years, 4 different countries, 4 different steel industry, 4 different countries, 4 different steel companies across a 44-year time period. So just to elaborate a little more, I started my career at British Steel Corporation in the UK. I was an apprentice electrician at 16 years old, and just on the far left there, I did a 4-year apprenticeship at South Bank Apprentice Training Centre. I went to technical college, on-job training, on plant, as well as going to school, and we did 5 placements between Redcar Works and Lackenby Works, both on Teesside. Redcar Works was primarily iron making. There was raw materials there, iron ore terminal, ore pelletizing plant, sinter plant, coke ovens, and the blast furnace as well. Lackenby Works was BOS, billet and slab casting, and actually on that location there was 10 rolling mills on that particular site. I was there, and a little bit about the culture at British Steel during my 12 years there. The mentality and the culture: fix it when it breaks, leave well alone. If it ain't broke, don't fix it. That sort of mentality. Purely reactive maintenance, mechanical electrical silos, waiting time, waiting for a mechanic, waiting for an electrician. Overtime heroes. I think we've all heard of those guys, the knights in shining armour that come in outside of hours and save the day, live for the callbacks. A lot of parts hoarding, people putting parts in the lockers, pulling parts from warehouses and putting them in their own cubbies, and little black books, keeping all the details to themselves, all the knowledge in a little black book in the top pocket, and having to do more with less. So some positive characteristics though. Some knowledge is power. Obviously, you know, tribal knowledge is a lot of what makes some of the industries tick. But if you don't share that knowledge, it's very dangerous. Obviously, people leaving, moving on. Some knowledge needs to be shared. Some centralized maintenance management system use was employed, as well as the early days of reliability-centered maintenance, failure mode and effect analysis, but it was very early, just the green shoots of that coming through. From British Steel, I left everything, my life as I'd known it. Prior to go to the Middle East, I went to Saudi Arabia to work for Saudi Iron and Steel Company. More the mini mill model with scrap recycling, melt shop, rolling mill. When I went there in '92, there was just one mill, a wire and rod mill. They built the second mill, which was a small section and bar mill during my time. They also built a flat products facility by the side of the existing mill, which was, again, scrap recycling, brand new melt shop, slab caster, hot strip mill, and a complete cold mill complex too. The mentality and culture during my time in Saudi Arabia with Hadid, very much a can-do approach, very positive. If it's not working, fix it fast. And everyone was there for the same reason. We were all there to make money. Key characteristics: very much state-of-the-art technology, no expense spared. Obviously multicultural. Proactive and some predictive maintenance was employed. data acquisition and trending on just about everything, a lot of trending. Very good operations and maintenance collaboration, planned outages and down days, and we did do failure analysis there as well. So from Saudi Arabia, after 10 years, my family and I were on the move again. We went to North America, to Canada, to work for Gareth. I spent 10 years in the mini mill in Manitoba in Canada, scrap recycling, melt shop, and rolling mill, again, electric arc furnace technology. 10 years in Canada in the Great White North, then I moved south to Minnesota, to the mill there, again, mini mill technology, scrap recycling, melt shop, and rolling mill. Mentality and culture within Gareth: analyze and own your failures and learn from them, and strive for continuous improvement as well. Know where you are and how to improve. Key characteristics: an excellent reliability program at Gareth. Maintenance and reliability annual assessments, they proved to be very useful in actually understanding what parts of the reliability process you were good at and which ones you needed to work on, and developing an action plan and a roadmap going forward to improve, and then being reassessed 1 year later to kind of see if you actually achieved what you set out to do. Very useful. Striving to improve towards world class. In any organization, I think CMMS use and the engagement of the employees in the CMMS system, whether it's SAP or Maximo, is key. You need your employees to use the centralized maintenance management system. And as always, continuous improvement, PDCA and STA cycles were pretty much standard within Gareth. So what did I learn on my travels? I learned to be very flexible. I learned to be analytical. I learned to be somewhat of a detective. It goes without saying in maintenance. Be predictive, be proactive, and be data-driven. So I saved the best till last, obviously. CMC, Mesa, Arizona. Our mentality and culture at CMC is pretty special. Safety above all. Try it and see. We're all entrepreneurs, and if you don't measure, you can't manage. And the key characteristics: the mills in Arizona are both micro mills, which is a continuous process. That's the difference between a mini mill and a micro mill. If the melt shop is down, the rolling mill's down. And if the rolling mill's down, the melt shop is down. So there's more of a focus on reliability than the original platform of kind of mini mill technology, because it's critical to the operation. So we're clean and green, very proud of that. We have a culture of reliability. We have top-down support all the way. Innovation and vision are supported. Very much an open door, one CMC approach. We embrace proactive and predictive maintenance. So why KCF? All of the above. The alignment between KCF and CMC was very apparent very quickly for all those reasons. We in Arizona, AZ1, a 15-year-old mill, and we were building AZ2, which is a brand new state-of-the-art merchant micro mill. AZ1's 15 years old. We saw the need for monitoring and measuring on some of the auxiliary systems like hydraulics, water systems, cranes, as was mentioned, bridge and different motions on cranes, some VFD applications, and definitely in Arizona, the HVAC. We need to monitor some of those. So we determined the need, floated that out to the team, met with some skepticism. You know, maybe it's just another thing that we need to maintain. It's something else to worry about, but it was quite the reverse. And contrary to popular belief, the first alert, the sky's not falling. You know, you put the system in so that you have a choice on your course of action when you get the alerts. So after a few wins, the skepticism fell away and it became part of what we do. So just general, acknowledge the need. Understand what part you will play, your organisation, internally. Embrace it and prepare your team. Give your team, you know, the heads up. This is what we're going to do and what it's going to look like. So discovering the value. The implementation, we implemented a pilot scheme in February 2023 in AZ1. It was a 3-month trial. We employed 68 sensors. As I mentioned earlier, auxiliary systems, pumps, fans, some crane applications, some temperature monitoring in HVACs. And it was at very low cost. Thank you, Dave. After 3 months, we expanded. You know, it was proven. We got a few good wins, and I'll talk about some of those in due course. We expanded to 371 sensors deployed on AZ1 in the melt shop, caster area, bar mill, water treatment plant, complete water treatment plant, cooling towers, everything was covered. And our critical cranes, a scrap crane and our 80-ton ladle crane. And as I mentioned earlier, the construction of AZ2 was well underway, and we started commissioning AZ2 in June last year. So August for deployment in AZ2 was ideal. Brand new equipment, established the baselines while the equipment's new. It was just an ideal application. We expanded to 322 sensors in AZ2. Again, melt shop, caster, rolling mill, and water treatment. So don't read this from the top down, nothing to do with the FDA. Read it from the bottom up. And this is our abnormality, defect, failure triangle. So definition of an abnormality is a measurable behavior change. A defect is a definitive fault mode that's presented itself. And a failure is an interrupted operation or production loss. So some real-time examples that we experienced throughout the summer and since the deployment. This one was quite a long story actually. We'd had a problem. The scrap crane is a critical piece of equipment for us. If the scrap crane's down, our melt shop's down, and hence the rolling mill and the whole process is down. We'd actually lost one of the hoist drives on this crane in an earlier event. We have a dual drive, and we were running on the backup drive, and we didn't want to lose that one, obviously, or we were dead in the water. So we employed a temperature sensor in the drive cabinet, and we got an alert this particular morning at 3:02, running on one drive. We got an alert at 3:02 via the cell phone app. And by 6:15 a.m., we were able to send one of our shift electricians up on the crane without interruption to figure out what was going on with the HVAC system up there, reset the HVAC, hence keeping the VFD that was running the crane cool. So very often the simple solution can be the right one if it aligns with your company culture and solves the real problem. Another abnormality, this one was in AZ2. This was on one of the water treatment plant pumps. You can see the alert there on March 27th, getting up into the alert band. We were able to idle the pump for a while until we were able to turn it off, split the coupling and investigate what the problem was. And you can't see it right there, but believe me, there's a plastic cap from a tube of welding rods. The plastic cap had gone through the water system and got stuck in the impeller, and that was causing the vibration. So that was a quick fix, pull the plastic cap out, and we went back to the unobstructed trend. Another abnormality, this one actually was 1 year ago tomorrow. We were actually at the KCF Summit last year with Levi and Tyler, our analysts. We did the labs at the KCF office, and Levi was so excited to show us some trends on our 80-ton ladle crane. There's 4 wheels on either runway for the bridge. 7 of the wheels the vibration trends were fine. 1, as he'd overlaid them all, was way off the map. He was so excited to show us. We were a lot less excited because we thought that we're looking at an 18 to 24 hour delay in the shop to replace a bridge wheel. We were like, oh my God. So, no word of a lie, we actually made a call to the plant. It was down day. We called a planner. Can you get a mechanic to go up on the crane? The mechanic went to that particular wheel, put 5 or 6 pumps of grease in that wheel. We were leaving that night, but Levi said he would continue to monitor it through the day. The plant started up at 7 p.m., and that trend came back down in line with the other 7 wheels. So it was a really good success story. So talking about abnormalities, if we act on our abnormalities, I mean, the first thing you're going to get is an abnormality. So you've got to take care of the abnormalities. That'll create less defects and ideally 0 failures. So acting on abnormalities, it's usually a low-cost predictive action, and it prevents irreversible or even further damage on an asset if you act on the abnormality. And it proves that you're embracing a predictive culture too. So moving up to the defect, this one was kind of a double-faceted, this one. It was both a temperature and a vibration issue. During the trial, during the pilot, our mold water pumps for the caster, we only have 2, and we need 1 running all the time during cast. And as soon as we deployed the pilot, it became apparent that on both of the pumps, the motors had looseness in the bearings. So we were like, well, we only have 1 spare, so what are we going to do? We're going to change the worst one. So this was the trend initially on the worst one, showing the vibration. We replaced the pump motor, and the vibration came back down to normal levels. So we sent the motor we'd just taken out for overhaul with the intent of replacing the second one when it came back. However, a week later, I got a call, I think it was a Friday afternoon, that this particular mold cooling water pump was running at 200 degrees after we'd changed the motor. And there's the trend. We were actually running at 200 F. We sent a shift electrician out Friday afternoon, spot temp checked the motor, and it was 200 F. So we had to modify the program so that we could run both pumps at the same time to allow us to bumplessly shut the bad one off, which we managed to do without interrupting cast. Shut the pump down, and the plastic fan on the back of the motor had kind of disintegrated. It would just blown to pieces. There was no cooling on that motor, and it had only been in use a week. So new doesn't always mean healthy. Just keep that in mind. I mean, it was a really good win for us, and it was in the pilot stage, this one. So it was the skeptics, when you show something like that, they totally get it. Another one, again, another defect, mill crane central hydraulics. You can see over time we're getting an increase in vibration. we hit the alert, and then we shut the pump down, split the motor and pump, and we found that the rubber insert between the two coupling halves, that had disintegrated, so we were running metal to metal on the two coupling halves. Again, a quick fix, split it, reinsert the insert, bolt it back up, and we're back to normal levels. So defects, you know, if we investigate and monitor defects, it allows for corrective action. It gives you a bit of time working with the analysts and on the solution and looking at the rate of change on either the temperature issue or the vibration issue. You're making data-driven decisions. It prevents process impact. As the examples showed there, if you know there's an abnormality or a defect, you can figure out a way to not impact the process. And it can also enable maintenance inspection adjustment. If you've got a piece of kit that maybe you have a defect on there, you might need to change the maintenance program or the inspection program to keep an eye on that or bring some planned maintenance forward. Finally, we're going to move to the failures. Unfortunately, you can't win them all, although we do try, we strive for that. The scrap conveyor in AZ1, that feeds scrap into our electric arc furnace. And as you can see, around January 21st, we got into the alert stage. We knew that there was a problem. By nature, this is on a shaker table, so the baseline vibration is set very high. Some of the shaking is filtered out, but we did have an issue with a motor, and we planned to change the motor, but we couldn't get to it until the following down day. So we had the motor staged, down days Wednesday every week. And as it says, we can't get to it until next week, but unfortunately, the motor failed the day before. So that was a failure. That was 6 to 8 hours downtime, but you know, we'd seen the abnormality, we knew there was a defect, we planned to change it before the failure, but we were a day short. So failures, what do we learn from failures? Obviously, root cause failure analysis and skill set building. Some could say it's character building as well. You always learn, right, through the pain. Solid preventive corrective actions. That's the idea from an RCFA. But the third bullet, the action execution is key. It's no good creating a really good RCFA, coming up with solid actions and then not doing them. You've got to follow up and make sure you actually complete the actions. Unplanned versus planned. The last example there, we planned to change the motor on down day, but it failed a day before. So that cost us 6 to 8 hours in downtime, plus the labour cost and materials cost to do the job. And what else do you learn? Ideally, to prevent repeat failures, you don't want the same thing happening again, right? So, we've worked on 85 abnormalities together, KCF and CMC. We've worked on 18 defects. And as you just saw, we've had the one failure. So collaboratively, desk collaboration, 104 events. I think that's excellent results. So just to close out, KCF offers you the opportunity to make data-driven decisions for your asset reliability. And finally, the choice is yours. Thank you.